Hello, everyone. Thank you for joining this discussion between myself and Nandita Dukkipati. My name is Brighton Godfrey. I'm a professor in the Siebel School of Computing and Data Science at the University of Illinois. And it's a great honor to be here interviewing Nandita. Nandita is a distinguished engineer at Google. She leads host networking there with work centered on delivering high performance for applications, including through innovations in low latency networking, congestion control, which is going to be the subject of our chat today, as well as telemetry, hardware and software transports, reliability of ML workloads, a wide variety of topics. But I think most relevant for this discussion, Nandita has been, through the years, a contributor of really fundamental advances in congestion control, all the way from her PhD through much more recent work like the Falcon system, which is a reliable low latency hardware transport. Nandita received her PhD in electrical engineering from Stanford in 2008. So welcome, Nandita.
Thank you, Brighton, for the kind introduction. I'm really excited out here to chat about congestion control and related topics. Yeah.
It's a really subtle, fascinating, subtly difficult problem. So I'm glad we're talking about this one. In fact, it's really been probably one of the top few most ever present problems in networking over decades. Ever since the Jacobson paper in 1988. So I would be interested in, how do you get interested in congestion control originally? What drew your attention to this long-standing area?
Yeah, no, thank you for the question. My interest in congestion control goes way back when I joined Stanford as a graduate student, and I was looking for a problem to solve for my PhD. And it was right around that time that Dina Katabi's seminal work on explicit control protocol, or XCP, had come out. And as Nick McEwen, who's my advisor, right, and I were discussing, Nick posed a very simple question that as link speeds increase and as network bandwidths increase, don't you think flows are going to get shorter and you'll have less and less time to actually perform control in terms of how we were thinking of congestion control at that time, in terms of usual increments and decrements to rates, right? So that question was so simple and yet so intriguing. And that set me thinking about, the bandwidths are going to increase. What should we be doing, right, if we were actually starting afresh? So that started me on my journey to congestion control. And as a PhD student, I mean, we were unencumbered by backwards compatibility, etc. We were willing to, I was, willing to take a cleaner slate approach. And the thing about the field is that it has multiple components, right? I have a slight background in control theory, so it has, you could go the angle of a little bit on the angle of theory. You could go a little bit. It has congestion control. It has real implementations in real systems, so you could go look at real implementations. So it was very attractive to me that it involved experiments, modeling, and some theoretical work, right? So, and then as I graduated from Stanford and, joining the industry, at first, it didn't occur to me until I joined the industry that the gigantic role that congestion control actually plays in the life of an application, right? It has the power to increase application tail latency, or actually get it down to short when network bandwidth is the constraint, for example. So and that revelation to me, I mean, I was just wondering that when I joined Google, why is everyone calling on congestion control problems? That was, whether it was sometimes in a cluster, or sometimes it was actually users connecting to Google. They were talking a lot about, at that time, TCP and CC problems when I came in thinking congestion control must be done out here. I should go look for somewhere else. But I kept going back to it because it does have such a fundamental impact on latency, right? And it's only through later in the years that I learned on the crucial role that it plays in sort of navigating the workloads on where in the spectrum we operate on efficiency, isolation, and performance.
Mhm.
Um, that kept me hooked onto and engaged in CC. Right from there on, I no longer try to run away from it and try to embrace it more wholeheartedly. Yeah,
So in your dissertation project, that was the RCP protocol that
right.
that came out of that early study that you were mentioning. Is that right?
Correct. Yes. Yes.
And that actually it's a very beautifully clean design. I like how principled it is. We cover it when I teach graduate networking. And I guess there were some important ideas there that were kind of foreshadowing, right? Like the view of the shift of viewpoint from windows to rates and the importance of latency.
Yes.
Kind
Yes.
of foreshadowed some important developments later that came in BBR and elsewhere. Did
Right.
that was it intimidating at all to you? Even at that time, there had been a long history, hundreds of papers on congestion control, and so much emphasis on a certain worldview, like a window-based design, for example. Was that intimidating at all to kind of shift things and look at the problem in a different way?
It was because no, thank you for the great question, Bryden. Yes, RCP was something that I worked on and developed as a graduate student, and it was intimidating and refreshing in sort of I guess two ways. Intimidating in the sense that well, I hadn't gotten much validation early on that
Mhm.
because it was a different way of looking at it. Right, you start with a rate and then you continuously get rate updates. It's no longer just a delta plus, delta minus, but it's very different from say how TCP's congestion control operated. So I think it was different in that sense and
Mhm.
intimidating, but it was refreshing in the sense that hey, when you think about it from the application's point of view, all the metrics that were used in congestion control before, minimizing packet drops or minimizing queue delays or maximizing link utilization, all great metrics from the network operator's point of view. But really, the applications, they just care about how quickly does my transfer complete, the flow completion time. So and looking at it from that point of view gave it gave me some more confidence actually that hey, this actually does make sense from the workload point of view. But I must say that it's only after I graduated and joined the industry that I realized that the completion time, right, whether we call it RPC completion time these days, or flow completion time, or transfer completion time, is quintessentially important. It is the currency that applications
Mhm.
measure their SLOs on,
Right.
right? Yeah, it was a journey, but intimidating at first, but somewhat of refreshing and a relief later on. Yeah.
So now you've seen these systems and how the protocol affects what I guess ultimately humans care about in industry over quite a few years. So I'm curious, how has what has changed with congestion control in that time at what during your time at Google?
Yeah. Yeah.
Has have the solution? I mean, certainly the solutions have evolved. Have the problems changed as well?
That's another great question. And so much has changed both in terms of the problems and solutions. Just let's just take the very recent history, or right. Even if you ask me a couple of years back, data centers were predominantly carrying, for example, storage traffic, which looked that's traffic to and from storage servers, right? The traffic patterns looked very different. While they cared about tail latency, it was not the very, very deep tails, because a search application, for example, yes, it spawns 100 requests, 99 of them come back. No one is going to notice in the search results that the 100th one is actually missing, right?
Mhm.
But the applications now, the 100p tail latency actually dictates the job completion time. It is super critical for workloads like ML. So the applications have changed dramatically. Actually, this is the first time that we are seeing such a great amount of compute traffic in the data centers, right? I think first time in several decades. And the second thing that has changed is actually our tolerance for putting in capabilities in order to eke out the last few ounces of performance, the last few milliseconds of latency. I
Mhm.
think we're willing to invest more to get that tail down, because not getting the tail down has wider implications, including keeping accelerators idle, which actually could be quite expensive, right? So overall, and there's a third aspect too, but overall, my take is, the problems have changed, and therefore the solutions must change. We are in a constantly changing landscape. Why should congestion control stay static when everything around us is changing, when the applications are changing? Uh, Another aspect of a changing aspect of these applications that has bearing on congestion control is reliability. Now, I don't mean reliability in the sense of just loss recovery and reliability from losses, but what the applications are expecting in terms of reliability from the infrastructure, right? It's no longer just best effort delivery. They're expecting much more and more predictability from the network. And therefore, all the things that we thought of as corner cases in congestion
Mhm.
control behavior under retransmission timeouts, congestion control behavior under transient faults in the network, congestion control behavior when losses and delays is not due to congestion, but possibly some other things happening on the system, like PCIe related errors or memory related errors that result in transient stops in the network traffic, right? Congestion control has to handle well in all of these scenarios, but um, just how we think about it and systematically going about responses of congestion control to these faults, right? I think are actually new things that are coming up. There is very interesting work to do out here, that driven by the increasing expectations and demands of the applications from networking.
So
Yeah,
robustness, it sounds like, is way more important now to these unusual situations.
absolutely,
And how do you
absolutely.
deal with that? Is that something you can understand those scenarios and design for it, or you have to kind of be prepared for the unexpected?
I think it's a bit of both. Um, it's a bit of both, because the first of all, addressing these scenarios is super important, especially in the context of ML,
Mhm.
wherein, as I was talking before, the 100p latency is important. If a single accelerator is not working, or if a single PCIe bus is actually acting out, it having errors, the entire workload is actually stalled or not making progress because of one PCI, some errors on the PCIe and network flow retransmitting, et cetera, right? So it's crucially important to address this. The second point is the problem is not static. The nature of the faults and the problem changes with hardware generations,
Mhm.
and hardware is changing with every new generation of accelerators, memories, NICs, etc. So I do think that we are starting to build a muscle by solving the problem, looking at the problems that are experienced in the current hardware. But we must go beyond in sort of generalizing the both the problems and systemizing the solutions. Right? I just don't think we're actually there yet, but I think it's a really ripe field for congestion control on handling transient or long running faults. Because when these faults happen, the first thing that happens is the network drops, peak the loudest in that. It's a symptom that just cries out every other. When any component fails, networking drops just come up, and suddenly it's congestion controls problem. Right? Even though it could be some random component in the system that actually failed and the network traffic is not making progress. So surfacing
You
those.
mean because there's effectively a kind of back pressure that happens?
Yeah, yeah,
Okay.
or its connection does not make progress, and
Mm.
it's retransmitting, but is not making progress. It nothing to do with congestion in the network, but the symptom comes up as congestion related issues, but disambiguating between congestion and these are, other non-congestion related faults, right? And both surfacing in terms of observability, but also what should be the response to a fault versus a congestion. I think is an important question to think through. Yeah.
So there's something that's kind of underlying a lot of this evolution of networking and congestion control specifically, which is kind of about how we evolve.
Hmm.
Um, and I think one of the struggles in networking that's um, in a way it's inherent to networks that we have to interconnect things, so there has to be some degree of coordination. And often that makes it hard to deploy something completely new. And I think that was true, especially at an earlier period of time in congestion control, that it was kind of ossified for a long period of time. Do you think that's still true, or can we iterate much more quickly now as a field?
Yeah, that's actually a great question. I'm actually increasingly, I think of it sometimes, and I think that there are sort of two eras, and there's a second era that we are going into. So the first era was, when we actually focused a lot of the congestion control work when the data centers were coming up. The data centers gave us incredible opportunity to be able to iterate quickly because now all of these networking, whether it's the sender, the receiver, the network devices in between the switches or the SDN controllers were all under the control of one network operator. So it was easy to change either, right? And it was easier than before, say, than in the internet to be able to incrementally deploy or to do forklift upgrades, right? So that capability really gave us this incredible opportunity to iterate, which I think is the single most important reason why it allowed us to make progress in congestion control. Because in
Mhm.
our field, we need to be able to do something, put it out there, look at our errors and iterate on it and make it better, right? Like no single person can get it right the very first time, put it out there, and voila, 100%, it works great. It never usually happens that way. So the power of iteration offered by the data center environment was, I think, very crucial, and it was mostly operating in using software stacks that were easier to upgrade and so on and so forth, right? But now, as we are moving towards more intensive compute intensive workloads and moving bits in networking is just getting expensive just doing it in software, and that's why we're doing more and more hardware offloads, and
Hmm.
that's what Falcon work that you had mentioned earlier, moving transport congestion control into NICs. So as we're moving into hardware, I do worry slightly that power of iteration is going to be slowed down as we're moving more networking functions and transports is moving more onto offloaded more to the hardware. But there is hope because thanks to much of the work in the community, in the networking community of programmability, right, is coming to the NICs as well, and not to and not just the switches. So I am hopeful that we will actually see, even if it moves is offloaded to hardware, we'll see more programmability that will allow us to iterate. Yeah. So thanks to the work from the community, I mean, I think all of the work on programmability, the P4, etc., has been pretty tremendous. Yeah.
And I think that's suggesting some research challenges in there as well.
Yeah. In,
Um,
yeah. Go ahead. Go ahead. Right. Yeah.
so I think a lot of the folks that are um, um, actually, hopefully, can do a little cut here in the video. Just going back a little bit, I did want to ask one other thing. So in the that evolution across time, there's another uh, step in the evolution process, guess, which is pretty interesting, which is the shift from the kernel to user space.
Mhm.
Can you talk about that at all? And also, how does that interact with the hardware?
Yeah, yeah. No, that's a great question. I can talk about it in the context that I very closely work with. For example, a lot of our workloads, traffic, etc., was carried over the kernel TCP, right? Using Linux TCP, and over time we realized that there are ways to build more CPU efficient networking stacks using spin polling, etc., and not relying on interrupts, and that led to the work on Snap that many that colleagues at Google started it, and yeah, right, we call it Snap and Pony Express. So that moved the transport functionality to user space using high-speed spin polling queues, etc. And that was a huge step function increase in both terms of CPU efficiency and the operates that were achievable, right? You're using a single core. But over time, even with many like years of optimizing even that stack, we clearly felt that actually we needed to move to the hardware offloads in order to get the next step function, both in terms of predictable latency, right? But also in terms of the operation rates and the software stacks were pretty good at driving high bandwidth for large transfers, etc. But when you have lots
Mhm.
of small transfers, they burn a lot of CPU cores, right? And those are expensive cores that we actually wanted to sell it to our cloud customers. We are in the cloud business after all, right? So that necessitated us to move into thinking about hardware transports in moving the functionality to hardware. But knowing that, and but knowing that it has taken years to actually optimize the transport and congestion control in software, we just knew it that everything cannot just be in fixed function ASICs in software, right? It was in hardware. It really was important to me that we distill out some aspects to programmability, and that's kind of where in Falcon we thought about the rate update engine, where we can it's a C++ program running on ARM cores, and we can actually change the congestion control, the load balancing algorithms, and some other decisions made with respect to loss recovery, etc. So that division between hardware and software was very important to us. Yeah.
So
And did I answer your question, Brighton? I feel that you had asked something else that I hadn't.
I think you covered it. Yeah. I was going to ask another question though. I think a lot of the folks who are joining us in this discussion are PhD students at universities, just starting out in research. And I think one of the questions is that a lot of us, certainly I felt when I was a student, was, is what I'm doing ever going to get out there? Does it matter? So this gets into, the interplay between what innovations happen in academia, what happens in industry, how they affect each other. So um, looking at what's been deployed at Google, are there ways that academic work has shaped it? Or on the other hand, are there ways that academic research is kind of going in the wrong direction, do you think?
That's a great question. First of all, no, academic research is not going in the wrong direction. Academic research has, I mean, 200%, 500% shaped what we do at Google, what I think at Google, right? And here are some ways, right? Some concrete ways, and then I'll give you other ways. Well, first of all, I think when we were developing, say, timely or swift congestion
Hmm.
control, I mean, look at the seminal work that has gone in from academia on delay-based congestion control, including
Hmm.
TCP Vegas and TCP
Hmm.
Fast, and all the analysis that was there behind it. I
Hmm.
mean, all kind of we did in the data centers is actually take the inspiration from that work and marry it with some of the hardware capabilities in data centers, like hardware timestamps, and realize that when those ideas are married with the hardware capabilities, wow, they can be turbo boosted. They do even better, right? So, and if Vegas and Fast didn't exist, and then it would have been a much longer route and much more winding route. So, absolutely, academic research has an impact. I think the way I think about it is it's less about this particular instantiation of Vegas or Fast is running in the data centers, but the influence that it has had, I cannot overemphasize it. Similarly, all the work that has gone with respect to HPCC, HOMA, P-host, NDP, ExpressPass, P-Fabric, the congestion manager, and I'm sure I'm missing like a lot of work, right? Has over and over found its ways in many ways that into different products, into different product discussions, into the considerations of what schemes we should do. So yes, so one thing that I can realize as a graduate student is impact comes in many forms, and some impact like this of influence can take a while, but it's undoubtedly there, right? The second thing I would say is that some of the theoretical underpinnings and the models that come from academia have been hugely influential, right? Like the works systemizing the proportional integral controllers and their role in active queue management schemes and congestion control, as well as the work by Frank Kelly, John Doyle, Stephen Lowe on the control theory behind it gives a framework, and some of the more recent work too that has come out from academia. It gives a framework to think about, else all we have are heuristics that could run amok, right? So definitely, and that's why I think the role that academia and researchers should continue playing. Please do not solve today's problems of the industry. I think the industry will do that in an incremental way, and we absolutely want the efficiency gains. We want those tail latencies to be tall. But I think actually let's think about what would be a new way of actually looking at it, something that industry is not incentivized to think about today, right? Because it takes a little bit of a deeper thinking and longer term, right? So, and think about the more of the fundamental trade-offs. Think about overlap between the areas. It's not just CC, but congestion control plus load balancing, congestion control plus reliability, congestion control plus scheduling, right? Think the whole thing is a resource allocation problem. So the academia has a role to think more holistically right, and propose solutions as some of these demanding workloads are changing their needs, right, almost every other week. Yeah, so I think that actually now has been as strong as ever, where research in academia has a strong role to play, and I would happily go back any day, even today. Yeah.
So it's not just about the code, it's also about, are you drawing out fundamental concepts that might become really important in a
Yes,
few years or even a few decades.
that's right. And when those are realized, um, know that a lot of things, when they work well, a lot of things become easier, right? It's less operational burden because they just work well. Um, so try and think of those very simple but solutions, but grounded in systemizations, grounded in either strong foundations, because they do go a long way. Yeah.
So what should a grad student right now looking for a dissertation topic be thinking about? Do you think congestion control is a solved problem now?
There is no way after this interview, I don't think anyone would say that I would say congestion control is a solved problem. It's broadly, it's a resource allocation problem, and as long as there are players, the traffic in the network and the applications are changing, I do think that we have to constantly rethink and redo this problem, right? I mean, so far, at least, we haven't found the optimal solution that works on sunny days, rainy days for any application without tuning it and without being an operational burden that just automatically figures it out. No, we're not there yet. So I would say continue. I would say couple of things. Take a step back and look at what the application needs, right? Don't come from it just from the problem of congestion control point of view. Study the workloads a little bit and see what do they actually want, and then what role does resource allocation play in there, right? And then look at how the interaction of congestion control with some of the adjacent areas, as I was talking about, including reliability, load balancing, right, handling faults, and or scheduling collectives. Look at the intersection of those areas, which and I think that there are a wealth of problems there to be solved.
Well, that's a lot of great ideas that you've left us with. I think we can leave it there and I'll go think.
Thank you, Brighton. This was it. It actually made me your questions made me think as well, and I'm even more excited to continue working in this area. So thank you.
Thanks very much for your time, Nandita. It was very inspirational. We'll talk again soon. Thanks.